with the talk of yesterday. So there was a slide that I did not find within the talk yesterday to easily. And this is a typical NMR image that you could get for the diagnostic. And this, in the NMR image, what you see is the intensity of the magnetic resonance of the hydrogen nuclei, which are in water. And typically, what you see is the intensity, and what gives them essentially the density is more or less constant. What you notice the difference is in the relaxation, because water could be even in a solid tissue or a more liquid tissue. And this is so in a typical image, you have they give you two images. This is T1, where essentially the contrast is given not only by the intensity, but also by the relaxation time. So essentially, whether the hydrogen is in liquid or in a solid, more bond tissue. And there is also a second image here, which is say T2. For T2, usually you take a gadolinium, so a contrastant, which is a magnetic nuclei that they put this in the blood. So when this gadolinium gets close to the hydrogen, then the hydrogen will relax differently. And essentially, what you are measuring here, again, as a contrast, is the essentially, as I said, the Hahn-Echo T2, that's what is being measured by Hahn-Echo, is the precession of a spin around the magnetic field. You make it to rotate backward and see what you recover. That's a time reversal of a single spin. But this single spin cannot be completely reversed because of the gadolinium, which is in the environment, and the neighbor spins. And this is the second contrast that you see. You see different details, different things, but typically you see more detail here. From the experiment that I show you, and I am going to show better today, where you do time reversal of a many-body Hamiltonian, then it is the many-body dynamics will add additional time because you sort of compensate T2, but then you see a T3, which is, this is not known yet, but essentially I have a doctoral student, former doctoral student who has Gonzalo Alvarez working in Bariloche. He has a laboratory, and he's developing techniques to do contrast in images. So this sort of many-body time reversal could be used to have still a further enhancement of these images. Well, that was a thing that we were left yesterday. Oopa. Many things. I don't know how to advance rapidly here. Let's see. I should have put this where it belongs. So essentially, the point where we left was when I show you the well, this is another thing that I wanted to essentially to comment that was left because of the question that appeared afterwards. Remember, I have here, this is a stadium, and this is actually a Lorentz gas, so an electron going in a Lorentz gas. So we do the time reversal for this one-body dynamics of a wave packet. And from this one-body dynamics, what we observe is this decay, which is the Lyapunov exponent. It is the Lyapunov exponent that coincides with the classical Lyapunov exponent. That's the point. So someone asked me afterwards whether there is what is the Lyapunov exponent in quantum mechanics. It's the same, the one as in quantum mechanics is this decay, and you do it evaluating the dynamics of a wave packet, the forward and backward dynamics. If you do the exponent, as a function of the perturbation, the change in the Hamiltonian, you first see a Fermi-Golden rule, which is essentially, this is not the, it is not the Lyapunov exponent for small perturbation. But once you exceed a critical perturbation, that different systems, because there are different energies, I think that's their stadium work at the different energies, then you reach the Lyapunov regime, which is there. Then you calculate, the way to calculate the Lyapunov exponent from quantum mechanics, the same that corresponds in the classical one, is again the quantum dynamics. Could be equivalent to do it in the classical system. And now, in the spin system, we don't have a classical correspondence. So there is not such a thing immediately as a Lyapunov exponent, unless these things that now in the OTOCs they try to define a Lyapunov exponent we are going to mention now, but it's really very much dependent on what are the operators that you are using. So it's not clear whether it will be a real Lyapunov exponent or not. That's essentially what I wanted to say. And that's why I say from a quantum calculation, if the perturbation is small, you are in this regime, which is Fermi-Golden rule, and then you enter the Lyapunov exponent, you obtain this. These are the classical exponents, that the classical values of the critical that are calculated. I'm sorry, these critical ones are evaluated by evaluating a Fermi-Golden rule with this perturbation and the Lyapunov exponent. So these things can be calculated from first principles, but knowing what is the perturbation and what is the classical Lyapunov exponent. Now, let's. As I mentioned, we have been doing a number of experiments. A number of experiments with a number of systems I'm going to mention again, like all of these. In particular, now I'm going to mention these two, which is the ferrocene, which is the one that I first Ernst did in his experiment. This is a symmetry, that's something else that we did, where we have rings, so the spins are in the rings, and this ring interact with these other rings, and so on. And cobaltocene is the same as ferrocene, but then you have a cobaltum atom, which is quadrupolar. So essentially you have, because it is quadrupolar, it's an local electric field, quadrupolar electric field, that is very much sensitive to vibrations in the system. So it's a connection with the environment, having quadrupolar nuclei. But otherwise, the nuclear spins are not connected to the environment. So you heard that these experiments are done at high temperature. High temperature means room temperature. It's infinite temperature for the interactions of the spin. However, these spins do not relax. Again, a question that appeared yesterday. It is as much that do not relax that essentially they could take a day to actually go to equilibrium. So you have to apply pulse sequences that you sort of make the spins DC, so you tumble from one side to the other side, so they became random in spite of not being completely relaxed. But essentially, there is not a T1 in these solids. It's a very long time. So essentially, quantum mechanical effect. And all the coherence that appears is the coherence that has to do with the interaction with the spins within themselves. They are their own environment. There is not a direct connection with the environment. That's quite interesting. It's a quantum mechanical, completely quantum mechanical many-body situation. And then let me show what is the tip of the Loschmidt echo as a function of time, of the reversal time. So as I show you in the ferrocene, which is the first that I show, this is a decay which is not an exponential, but rather an Gaussian, you are going to see later on. This is a system which is completely isolated from the environment. There is no interaction with the environment. And here you have this manganosine, that's a single ring, and then you have this manganese nuclei, which is also paramagnetic. And this is much connected with the environment. Again, because you have a spin that is connected with the environment. Manganese is paramagnetic and quadrupolar. And then in the case when it is connected with the environment, you see a decay which is exponential. And this is a Fermi-Golden rule. It's a time scale of the connection with the environment. We couldn't do change at the time. We didn't know how to change the time scales here. But essentially, you see that there are typically two kinds of behavior. Gaussian, when the time reversal occurs in a system which dynamics which could be mostly unitary. I'm going to discuss a bit more later. And this is in the case when the many-body time scale is longer than the interaction with the environment. Here, the many-body time scale, which could be essentially, let's say, T2, it's shorter. That's more dynamics than the interaction with the environment. That's the situation that we are. So what essentially is at stake in this experiment? Essentially, is the creation of a non-equilibrium local polarization, the evolution of a system with typically a dipolar Hamiltonian for a time. Then we do a time reversal evolution with a minus the Hamiltonian. Why it is that? Because the Hamiltonian is a dipolar Hamiltonian. And what is a dipolar Hamiltonian? I always think the dipolar Hamiltonian as a Heisenberg Hamiltonian, where you have terms which are Ising terms and flip-flop terms. The only thing is the dipolar Hamiltonian is the sign of the Ising terms is twice the coefficient and than the terms of the flip-flop. So essentially anisotropic. In the Heisenberg interaction, whatever interaction with direction you have is the same. That because it's like a scalar vector between the product of the two vectors. But in the dipolar, it's different this than this. And this is what allows us essentially to do this time reversal, the point that it is a dipolar Hamiltonian. Yes. Mm-hmm. That's essentially like a grain of salt. 10 to the 23 for sure. 10 to the 23, that's more than the Avogadro number. That's really macroscopic. And even when it is that 10 to the 23, they are almost isolated with the environment. Why it is? Because the molecules are rotating inside the crystal. So essentially, they average any effect by rotating. In a liquid, also you see you are able to do this quantum computation with molecules in a liquid. In a liquid, it's the same. Similarly, in a liquid, the molecule is moving around so many times in the time scale of the slow quantum dynamics that the environmental effects gets averaged out. So that's why in a liquid you see a line which is very narrow. And again, in a liquid, the molecules is quite isolated, not as much as in these crystal solids. These are the time scales. Well, now I'm going to show a few more experiments. As I say, this will be the calculation with 10 spins, so do two rings confronted that you will see this mesoscopic echo of Poincaré recurrences that has to do, what are the recurrences? Essentially, the excitation goes around the molecules and goes back to the initial site. That's essentially the recurrence. The excitation splits in two, goes around the ring and goes back. And essentially moves from one ring to the other, and that's why we don't have the strong echo that we will see in a single ring. And here we have a different, at the beginning, we have this solid state mentality. They say, okay, we want to change our dynamics, then we have to change our system. Change our system is to change the molecule. Also, to put the molecule, the crystal at different orientations. That's because the interaction between the dipolar interaction depends on the angle between the two spins and the external magnetic field. There is a cosine there that allows you to change even the sign of the interaction. So by orienting the crystal in different directions, you have different Hamiltonians, which is essentially scaled down. And this essential here, there are two Hamiltonians, one that with interaction which is 2,600, and here 3,200. And you scale, now you refer the time to this interaction, and essentially it is the same. These are different orientation. For that, we have to do a crystal. This is the forward in time dynamics. And when we do the backward in time dynamics, this is the Loschmidt echo, the local Loschmidt echo in the many-body system, we always see the same decay. Again, the decay does not only depends on the dynamical parameters on your Hamiltonian, not in anything else, not in the errors that you have. Again, another that we do, there is another thing that we can do is again to put the system in different magnetic field, the different strengths of the magnetic field. That's a bigger magnet, a smaller magnet, because the size of the magnet, the Zeeman interaction, decides how important is your internal interaction respect to the Zeeman energy. So determines the truncation, the errors that you're committing. And with that, not only this error, only you are using different frequencies. Here it is H1, that's, you don't see, it's not clear. H1 is the strength of the radio frequency field that you use. Essentially, you're irradiating the system. And so the spins, the spins rotate around the magnetic field. And you're irradiating with that frequency of the external magnetic field, but then with a strength which is variable. And since you are following with the radio frequency, you are following the spin, then you will have a Zeeman energy in the field of the frequency. So it is very important, the strength of the frequency, and also is what will determine the sort of truncation errors. And here we have different truncations, and essentially those points lie more or less in the same region. This is the decay of the Loschmidt echo, the decay rate of this Gaussian, as a function of this radio frequency strength, which is essentially omega-1, that determines your possible errors. So essentially, if I don't have errors because I will have a sort of, ideally, an external field that will do perfect truncation. And all our data are here. That's different crystal orientations, different magnetic field, different radio frequencies, and all the data are here, never here. That's a mystery. So all people in magnetic resonance for like 40 years, 50 years already, they started to determine the, and I don't know why it's not reversible. Why this is this huge amount? Because the perturbations is very small, and it's not interacting with the environment. So as a question, that's why we're studying the Loschmidt echo all the time. Because we were expecting that something that you will go to there, like this. And then with that family of experiment, that's when we started to conceive the idea of this central hypothesis of irreversibility, that this reversibility depends only on the Hamiltonian and not on the environment. This is the environment. Zero environment, big environment. Environment as given here as an error in the truncation of the dynamics. Well, then we have those systems. We started to realize, I mean, our mind started to realize and say, okay, we must do something else with the Hamiltonian. And then what we decided to do is sort of decrease the strength of the Hamiltonian by doing the following. We do forward in time dynamics backward, forward backwards. It's like not allowing the Hamiltonian to fully develop. That's we call this pulse sequence, we started to new mentality, reduce evolution of the polarization echo, REPE. And here we have this system where we have cobaltum atom, which is a connection with the environment. We started with this molecule with a crystal, and then we reduced the Hamiltonian by this pole sequence. And as we reduce the Hamiltonian, we finally see an exponential for the decay of the Loschmidt echo, an exponential which is essentially dependent on the environment. Again, this depends on the environment because we have this quadrupolar nuclei. We go from a situation where the coherence or irreversibility depends on the Hamiltonian to a situation where it depends on the environment. That's because we have an environment. And now there is a second question. That's what happened with the experiment of Ernst. In the experiment of Ernst, someone asked me yesterday why it was that Ernst was observed this exponential here. And then he said this value that was mostly one half. This is time for the polarization. That's forward in time dynamics. He will observe this. What happened is that he forgot the dynamics during the cross-polarization, during the transfer from the carbon to the proton. So there is a dynamics is what's involved here. The dynamics started before. The quantum dynamics started here, but they measure here. Once to transfer the polarization to a proton, you have to do this. You have to use the Rabi oscillation. You are in the carbon. You have the polarization in the carbon, and then it's a polarization in the proton when you started in the carbon. Then the way is you will have an oscillation like this, and I'm sorry. No, just the opposite. Yes. Sorry. You start in the carbon and they go to the proton. That's just the opposite. You go to the proton. You are in the carbon, and then you go to the proton. Then you are in the carbon. The polarization in the proton, which is the system that you are studying, you will have through the Rabi oscillation. This is a swap gate. That's now standard in quantum computing. And then what you do, you stop here. And this is your initial, that's supposed to be your initial time, like this. But actually, during all this period, the polarization already has, the evolution in the proton system already has started. And that's why he missed this part. And started with this that looks like an exponential, but actually quantum mechanics is quadratic, as always. It's always 1 minus the interaction between the carbon and the proton squared times over h bar. That's the decay. That's always quantum sigma effect. So he saw this. Since he saw this, all the data are normalized to this and not to this. So this 1/5 is not 1/5. And on the other hand, they put cobaltum in the crystal in order to do a faster experiment. When they grow the crystal, they put cobaltum impurities, that this prevents coherence. Though essentially, that's why they didn't see the Poincaré echoes, the mesoscopic echo. So you see how many details they have to do. It took us years to really realize what was going on. Yes? And that's the number of pulses that we do to reduce the Hamiltonian, while we cannot reduce the interaction with the environment, with the cobaltum. So we are reducing, say, this without reduction, and then further progressive reduction of the Hamiltonian. While, for example, then, if we are in the ferrocene, which is no magnetic impurity, this is a crystal we grow without impurities, we change the Hamiltonian, and we always see these Gaussians. This decay, and essentially scale with the Hamiltonian. Here, n is the inverse strength of the Hamiltonian, with the weaker Hamiltonian, and the time scales is longer and longer proportionally. That's linear. So essentially, the reversibility time scales goes with the Hamiltonian and with anything else here. That's the difference with an environment and without an environment. That's for us. That's just the starting thing, but essentially what give us again, in a single crystal of ferrocene, we see that everything scales. In some point, we did this, we wanted to dilute this molecule. We say, okay, let's dilute the molecule. So essentially, we put we made this crystal with carbon-16, and then we put the molecules in between. So they won't see each other, the spins. So we have only 10 spins, and then another group of 10 spins, and so on. And when we do the Loschmidt echo there, essentially we easily see an exponential. Again, start to feel somehow the environment more than the dynamics. That's essentially the sort of curve that we have here. That's essentially, in that case, is not controlled by the dynamics, but because there is not a real many-body dynamics, just 10 spins. 10 spins within the molecule that are seeing each other, and the other spins, there is always there, but essentially it's a longer time scale. And that's, again, that's the experiment. This is the ferrocene, and this is essentially this exponential is more or less the ferrocene diluted in carbon. But then we started to get cheers that for many years we started to look more or less these sort of things, liquid crystals and other systems where we could have less spins to see, not to be directly in the thermodynamic limit, but now the idea is will be to change the perturbation from some other ways. Okay, so essentially, the only things that are left in the Hamiltonian that we are not able to invert are they are called the non-secular terms. The dipolar interaction also has the possibility to do the flop-flop and flip-flip process. But this process, flop-flop and flip-flip, will change too much the energy because it will change the spins in a Zeeman energy. So essentially it's truncated by the Zeeman energy. So the non-secular terms, essentially, there are just perturbations on the Hamiltonian, on the flip-flop terms, and the Ising terms that essentially they are energies. And those are the ones that are proportional to this radio frequency field that I was mentioning. And then that's why we arrived to this, the central hypothesis of irreversibility that I mentioned. All this data until now, they are here and not there. And this looks quite, for me, quite as a resistivity as a function of temperature, which is the environment that we go in this sort of regime. So the hypothesis, the perturbation is in perturbation-independent decay, which in this one-body system, it's only the perturbation-independent regime, that is the Lyapunov regime, is only obtained when the perturbation is above a critical value. But the point is, because of the thermodynamic limit, is that this critical value in a many spin system, because it's a many body, like it occurs, the critical value goes to 0, as I show you from the Lorentz gas before. That's essentially the hint that needs to be proved. For me, more or less, the role of the many-body interactions is like in a mixer. I took this, I learned of this when I was a student from a Scientific American article. That was an experiment that Erwin Hahn used to do in Berkeley for his students, and it's in Scientific American. It is the rotating mixer. You have 2 cylinders of glass. Inside there is your glycerin, some sticky oil, and you put a column of tinted glycerin. And you have a handle, and you start turning the handle. After 20 turns, essentially it looks mixed. Looks mixed, but you know, if this is mixing, if you look from above, it's not as much mix. As you see, if you do the handle backwards, that's a photograph from the sequence of Hahn. The way to think that is of course, that when you do the mixing, you are doing this sticking. So I was not able to do a simulation backwards. But my point is that once, if you mix enough, so this is not the experiment that complete as Han did, but if you do the mixing, but very, very, not 20, but 1,000 turns, you will not be able to come back. You will not be able to come back. Here, I have this. No. If the distances between those rings is divided by n is bigger than the diffusion length, then it will be completely mixed, blur out, and then you will not be able to come back. So for me, the many-body dynamics, that is the chaos, what does is this mixing. So once you do the mixing, you are not able to come back. That's the situation. That's what you do essentially when you put sugar in your coffee. You put sugar, and you don't wait that it diffuses. You just stir. So essentially, you will drink. Once it is stirred, you will not undo the sweetening. That's essentially, at least intuitively, the idea. So as I mentioned, we started to think another tools within NMR. I said, this is my Hamiltonian. Look, this is the Heisenberg Hamiltonian, but the dipolar has an extra ZZ component, an extra Ising that compensates this part of the Heisenberg Hamiltonian. And essentially, you have an angular dependence, which this is the angle between the two interacting spins and the external magnetic field. And then with this Hamiltonian, you are able to sort of put the spins in different directions so that you have different Hamiltonians. You can tumble the spins. That's the new concept. Now, the new concept is that is now standard is using the Floquet Hamiltonian. You make the system to have a Hamiltonian during a time, a Hamiltonian, another Hamiltonian, another time, and so on. This is the Floquet idea. You do this periodically, and so the system evolves under a periodic Hamiltonian. And in that case, you are, for example, able to build a double quantum Hamiltonian. You use a dipolar Hamiltonian along y direction, a dipolar Hamiltonian along z direction. You use it with different signs, and you build flop-flop and flip-flip Hamiltonian. That's a double quantum that essentially, again, does not conserve the polarization. Until now, the experiment that I showed you before, they were dipolar Hamiltonian evolving in the magnetic field basis. So the polarization is always conserved. So you have flip-flop processes and interactions, but these interactions do not change the total number of the spin projection. That was going to be a diffusive process. But if you have this Hamiltonian, then it's no longer polarization conserved, but you start with a given polarization and will start increasing and decreasing the polarization because you have these terms. And this will occur if you do this process not in the basis of the external magnetic field, but you have to do in the basis which is perpendicular to the magnetic field. So you have two spins oriented that, and you do this, flop this, and in terms of energy, is the same. So it's difficult. I mean, I could try to do this more mathematically, but you won't learn more by seeing the mathematics of this, and it will be very, very long. But it's confusing in a bit. What you see there? I see a cow. So our main results until now, essentially, we were doing this always. We are having a many body states. Half of the spins are up, half of them are down. I create a polarization, let's say, locally. That's what we learned from the first experiment from Ernst. We do an evolution forward. We do an evolution backwards. And then we measure again whether it is up or down, whether whether the polarization returned to the original site. We learned from this Ernst experiment because we have the local carbon. And we didn't realize that actually this was very general, this situation was very general. And in general, in the cases where we don't have the environment, the decay will be with a Gaussian. And this Gaussian, I didn't stress in the previous talk, but essentially it's a Gaussian for even 3 orders of magnitude. In the cases where we take weeks measuring, the decay goes into we have to do a lot of average in order to go over the noise, and we were able to see 3 orders of magnitude for this Gaussian. It's not usual. That's quite exceptional when we do this experiment. And then the subject became hot. Essentially, that's about this information scrambling. I'm going to mention a bit. Essentially, because the high energy people and this cosmology, they associated they said that close to a black hole, the system will be maximally chaotic. Why? Because 2 particles that are falling into the black hole that start very close, they will be far away because the difference in gravitational field will be so different that will be very unstable. It's the same idea at what we put a particle on top of an inverted harmonic oscillator. It's unstable. You put two particles very close and they end up very far away. That's the idea. That's the strong interaction. And they needed this strong chaos in order a quantum theory that will be able to describe a quantum field theory that will be able to describe the classical gravitation, Einstein classical gravitation near a black hole should be chaotic. That's what they expected. And then they wanted to sort of quantify this quantum field theory. That's what the idea essentially started with Maldacena and Susskind and so on. And in their theory, what they consider it was a field theory. Essentially, was anti-de Sitter space. That means a universe which is confined, and this is the confination of the mirror in it's a universe in a box, and this in the center will be a black hole. And they say, okay, the instability, which is essentially proportional to the thermal, that's the temperature, and the temperature is related with the gravitational strength of the black hole. That's the Hawking radiation, and that will end up. Well, that's when I sort of get, and then these issues started to get, among the people who started to do this calculation, essentially, there were, for example, Susskind, Stanford, Roberts. They got they think, and they started to calculate the spin systems. Here, this Ising term. This is a spin in an external magnetic field, and another projection of the spin. They use this notation Z instead of IZ or SZ that I typically we use in magnetic resonance. And they see how essentially this will develop an excitation which is local in a spin system will start spreading into a number of sites as a function of time. That's the thing that they wanted to compute. And they did that with this with out-of-time order correlations, which was quite unclear at the beginning until actually Kitaev was able to clarify these things. So here Kitaev invited me to Caltech, and we have the fortune to discuss quite a few days. So the point that Kitaev realized that essentially these out-of-time order correlators will be related to something that was discussed before by Larkin-Ovchinnikov that I mentioned before. So Larkin-Ovchinnikov, in the context of transport in disordered metals, he discussed that how will be, if you start with a given value of an operator at time 0, what is the value at a time t, how essentially will change, could be different directions here, for example. So this will commute at time 0 because there are different directions of the momentum. But because the dynamics starts to mixing it up, then they no longer commute. And to evaluate that, they realized that it is given by the classical instability of how does the momentum changes when you have a small change in the initial conditions. That's essentially the stability coefficient. And you use this stability coefficient, which is proportional to the Poisson bracket. You use in the commutator with the H var, and then you take the square, and you see that this instability will manifest in the square of this exponent. That's, this is taken, I did a copy of Alexei Kitaev transparency. Here we are discussing these OTOCs and multiple quantum coherences that I mentioned. And he said, okay, this object will grow exponentially. That's the idea of the Loschmidt echo in Kitaev's talk. Okay, that's, here essentially this is de Hooft who introduced the first idea of the sort of instability close to a black hole. Then let's see again what we are studying. I said having many body state, create an excitation, forward in time, backward in time, detect the excitation. If you rewrite this, you see essentially you can put, and you write now a perturbation that does not act during the whole backward in time, but a perturbation which is a delta function in time. So essentially at the moment you do the time reversal, you put the perturbation, only just at this time. So if you do just the perturbation is at this time, this perturbation is this operator B. Could be later on we are going to put a rotation, could be a phase, for example, could be a local phase, a global phase, whatever operator that acts locally in time, after time t, and then you do the backward in time evolution, and then you measure your system. Then it is clear that an OTOC is the same thing that we have, it's a related thing to what we have been measuring. That's, you do the perturbation at a given time. And then you normalize this. And then you can write this, our Loschmidt echo, in the form of an OTOC, of this OTOC fidelity. This is just the linear term, not the commutator. But then this is what we are going to, I'm going to explain how to do again further experiments, although I will go a bit backward again, something that I could have said before. Like 50 years ago, everything was done with the standard experiments were essentially continuous wave experiments. You throw light and see whether the light is absorbed by a system or not. For example, that will be absorption. So essentially, you have a sort of motor. You have that's what you are seeing traditionally. You apply throw microwaves into your system and see whether it is observed. You could see it as a peak or as a dip, depending on what you are measuring. That was the traditional thing. But then it appears Richard Ernst, that's why he won the Nobel Prize, with a Fourier transform NMR that consists, given strengthening this oscillator or giving a kick to the oscillator. And if you give the oscillator a kick, then you will see how it oscillates. And from this oscillation that you observe, you take out the relaxation rate, which is this width, and what is the frequency. Then essentially, nowadays, all the spectroscopies are done with with the kicks, not throwing continuous waves. Even light, you send the pulses of light. That's what you do typically now. So in a magnetic field, in NMR, what you do essentially, you have the external magnetic field, you have a spin here. This spin will rotate in the presence of the magnetic field in the prism, but if it is along the magnetic field, it is here. Then you apply the magnetic field in a perpendicular direction to this. This is the radio frequency. This is the external magnetic field. You put the radio frequency, and then you stay in the rotating frame as a spin that will go around this. So essentially, you have initially, your magnetic field is here. This is B0, you have this spin. And you apply a magnetic field here, B1, that's a radio frequency, that starts to go to the plane. But then this keeps rotating together with the spin. So you will see a spin that goes like this until reach this plane, and this stop irradiating the system. That's what you obtain. You have the initial spins, goes down, and you stop there. This is a pi/2 pulse. That's when your experiments start. And that's essentially your kick. Once you do that, the spin will rotate and will create, and it's not, no, it's not here. And then once you go there, you stop this irradiation and you start the detection. Here you have a wire and you see the detection, and you will see that the spin is rotating and will induce a free induction decay, a signal in this wire, which is oscillating as I showed you before. From this signal, you see what is the decay time, what is the frequency time. Why do you have a decay time? You have a decay time, as I mentioned yesterday, of the Han echo, because every spin that you do for all the spins simultaneously will see a sort of different local field, and so they will separate like the runners I mentioned before. So they spread, and that's why you see the oscillation in this decay. And then that was the Han experiment, what he did now explicitly in terms of pulses. It had a decay, which is this is actually an oscillation, a free induction decay. And then he gives a pulse here, a pulse over P, pi, that makes all the runners go backward in time to the original point. This is the Han echo in terms of pulses. You have applied radio frequency here, wait, and then apply radio frequency, and see what is the signal that you recover. But now, the signal that you recover is somehow still lost by the interaction between the runners, and this is why you see T2, which is the time scale at which the spins interact with each other. That's why the T2, the image that I show at the first spread, is the interaction between the spins, the time scale. But now, in the Loschmidt echo, what we do, we also invert the interaction between the spins. And we also have mounted a Han echo. So essentially, we don't have the effects of the spreading, or the local spreading, and we don't have the effect of the spin in between of them. That's why we should be able to recover the whole signal, but we don't, because it's chaos. So let's me understand a bit of the scrambling with a Hamiltonian. So essentially, the way to think of this is all the spins. I always think that's a good thing that I learned from Ernst to think in this local image. So I think that half of the spin are up, half of down, but then I'm sure that a given spin, which is perhaps this one near the carbon, I know that this is up. So I always think in terms of this spin. People in MR don't think like that, only think in all of them. They say, okay, these spins, they have this small polarization. So there is a probability, as I say, one in 1,000, that there is an extra orientation along the magnetic field. That's very small. So instead of people typically think in terms of the sum, everyone is 1 in 1,000. I think, okay, no, that's instead of having the sum, I have only one. And let's assume I have this double quantum Hamiltonian, which is the flop-flop and flip-flip. So this Hamiltonian finds the spin which is up and detects whether it has another up neighbor, then does the flops both down. Then you have this, and in the whole system, it finds another which is up, and then it makes it to go into the down direction. And then again, continues acting this Hamiltonian with all the pairs, and essentially this correlates with another, which typically these are in the whole sample 23 spins. Sometimes you have one which is down, and you can have either on the side you can have this, or you can have this one. If you have this one, then you do another process, flop process. So you start correlating the spins. And how do you write this correlation? Essentially, there was some of you that are doing the dynamics. Essentially, you have this initial excitation, so I put only the excited spins up, and the other is just my one in my density matrix. And the evolution of the density matrix in the presence of the Hamiltonian is the commutator of the density matrix with the Hamiltonian. So essentially, you start with this spin, and then because of the commutator, for example, this commutation, you end up having two spins correlated. That means you have these two are correlated. And then you do another commutation of this state with another Hamiltonian, then you go to 3, and so on. You're increasing, as time goes on, this initial information that you have in a single spin starts spreading in a cloud. That's already the idea of the out-of-time order correlators that you start to see this. And you do a further, another step in time, and you end up with a big strings of spins excited. That's a cloud. From every single spin, you go into a cloud. It's quite interesting. For me, to understand this was possible because I started with this local spin which is close to the carbon. Otherwise, I would not have understood this process because it occurs simultaneously in all the crystal. But if I think with a single initial state, which I always call 0, that's why I'm able to understand this. Then there are created correlations. Let's assume this as the simplest many-body state. That's up, 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 down, down, up, down, down. That's the density matrix. So essentially, in the diagonal of the density matrix, you have these, which are the occupations, the populations. And outside there are the coherencies, that relation, because of the dynamic, you related this state with this state because of this, for example, these flop-flop or flip-flip transitions. They are correlated. They are part of the same state. That's a complex state. And the point is, will be try to measure these things which are out of the diagonal of the density matrix. How do you do that? Essentially, these are what you call the multiple quantum coherencies. So essentially, I have the whole Hilbert space, I divided. What happened? There must be some. Is this? Let's see. Oh. No, I'm sorry. That I don't know what did I did. Again. No, but we ended up with the same problem as before. Let's see. Okay. Oh, but I am that. Do you know how I progress without that's a problem to having too big thing. Well, we are close. That's where I was. So essentially, there are different subspaces of the Hilbert space according to total spin projection. Here it is a spin projection minus 1/2. Means that in a system with 5 spins, there are 5 minus 1/2 and 2 1/2. That's essentially the Hilbert space. And this is another part of the Hilbert space with all these levels. You ask me, how are these energy levels there? They are Gaussians. Gaussians of width essentially given by the second moment, the local interaction. That's the Gaussian that you asked yesterday. So, but now the interaction starts mixing this because you have coherencies. That is no longer, you don't live in this part of the Hilbert space, but you live in combination because of the Hamiltonian and the combination of this with this other. These are the multiple quantum coherence, and you call these coherencies according to the number of spins, the projections of spin they relate. If they relate two flips, that's a double quantum coherence, like a double down or up. If you change in 4 spins projections, then you are in 4 quantum coherence and so on. So you call quantum coherences what are the distance in the Hilbert space that are being mixed in this collective state. That's essentially the name. Now, that's what you're doing with the Hamiltonian. Again, let's assume a linear chain here. I have a single spin which is up. The Hamiltonian finds the one that is down and then puts the 2 ups, and then you start increasing, the information starts spreading within the Hilbert space. Starts spreading within the Hilbert space. While it is doing that in the signal, you see as a free induction decay, which essentially that is decaying because these local spins are essentially spreading and going around, and then you see how do they decay. That's a typical thing. But while they do this, that's what you see, this is also happening that the spins are correlating and becoming a superposition of multi-spin system. That's you're becoming, the system has become entangled. Before it was a mixture, but because of the dynamics, this spin becomes entangled with a neighbor and with a neighbor and with a neighbor. That's become entangled, a bigger and bigger system. That's what you're doing. This is essentially becomes, more clearly when you do have these terms. Also, this term will entangle the spins, but within the given subspace of the Hilbert space. This flip-flop, the spin projection terms also entangle the system, but within the Hilbert space. But it is very important for us now to have this term that will mix different spin projections in the Hilbert space. Why? Because the points show you're spreading this excitation. Because what you are going to do is the following. You have the initial state. You make it to evolve in time, at a time t, and at a time t, you sort of applied, think that you applied a local magnetic field, temporal pulse of magnetic field, that gives a phase, a Zeeman phase, to the system. So this is essentially a Zeeman interaction proportional to some external magnetic field, and you will have a phase that depends on the total spin projection. So depending on the total spin projection of this cluster, you will have a different phase. So you will have a different phase if you have a single spin, than if you have 2 spins, that you have 3 spins, because it's having a phase that is proportional to the spin projection of this component in the Hilbert space. That's what you do here. You do this, you apply the phase, I'm sorry. You apply the phase, and then you undo the dynamics. You apply the phase, and then you undo the dynamics. And to undo the dynamics to see whether you have an excitation. It has spread. After it has spread, you apply the phase. And then you unspread. You do the backward in time dynamics by changing the sign of the Hamiltonian. And you see what is the observable that you have. And this is what is called a multiple quantum coherence experiment. Why? Because you will have a signal. Now is the time reversal. Assume that you have a perfect time reversal, because I forget now of the errors. only think about the perturbation that I do by applying the phase. Then, in principle, will reach, if the phase is 0, I will reach the perfect initial state. But if the phase is different from 0, I will have a phase that depends on the spin projection that I reach because of the dynamics. Then what we do, we didn't invent that we use it. What we do, we apply different phases, and for each phase, we measure the signal. For each value of the phase, we measure the signal. And then we Fourier transform with respect to the different phases that we put. We do different experiments. So we will have information of what the component of the different spin projections we have reached at a given time. So in a time of evolution, I went something that changed my spin projection in 2, in 3, in 4, in 5, but all of them occur simultaneously, and all of them, when you do backward in time, codify the information into, again, the initial excitation. So you codify, again, into this local observable, all this many-body space. And then what you do as I mentioned before, this is having this perturbation operator in the LE&OTOC, it's just this phase. And we have the phase codifies on the total spin projection of the reached by the excitation. And essentially, this observable is precisely the out-of-time order correlator, the square of this commutator of the system. So essentially, let's go to see a simple example. That's essentially how it was conceived. That is, essentially, we have the initial state, we put the phase, I think I have initial phase, evolves, I put the phase at a given time, I measure and do the backward evolution. No, the measurement is always after the backward evolution. I excite, I evolve with the Hamiltonian, I put the phase, I under-evolve, and I measure. That's what I do. And this is seen as an LE&OTOC. So the initial state, which is a spin projection here, the cluster size, and this is the number of spins. The number of spins has been have this flop-flop. This is for 2 spins because the Hamiltonian goes in pairs. I said impaired numbers, odd numbers before. Goes in pairs. At a longer time, you can go to 4, to 6, to 8. That's essentially like leaving a particle in this Galton board because it's having time to spread more and more and more, exciting further and further spins. I do the time reversal, and I codify each component in this Galton board is codified with a phase, and then I can, with a Fourier transform, I can know how is the Gaussian, the law of the big numbers, the Gaussian distribution for the polarization. This is one of the experiments that I show. That's an experiment already we correlated a huge number of spins, you see here. And this, the amplitudes of the Fourier transform is saying how many spins have been correlated in that given dynamics, in this given time of the dynamics. So that's scrambling. The initial information has scrambled between, so I don't have it here the edges, but you see that it goes in 2, like a huge number of numbers. Sometimes, this is the coherence order, which essentially says how were you able to reach the bigger situation that you're able to. You start with 2, then you have 4, let's say, that will be just the edges of this. The bigger and bigger the numbers that you reach, the correlations are these arches in this curve. Now, sometimes in some molecules, depending on what the crystals or so on, sometimes it's not like a Galton board because it stays too close to the initial site. That's essentially will correspond to this situation, and then you have the spreading more even. Because, I mean, if the molecule has some inhomogeneity, they mix together very well inside the molecule, and then you start to see spins which are farther away in the whole crystal. So let's again. In the situation that I have here, that's another organic crystal, adamantane, which is related to diamond. Essentially, you see the number of correlated spins go here, and it's already, I have the plot outside, goes like 3,000 or 4,000, very easily they get correlated. And the information says a part that does not spread too much, stays around 12 spins that correspond to the molecule. So in the molecule, essentially they correlate before reaching other parts of the crystal. But once it expands, we reach here until more or less 4,000. Weak cases that we reach 10,000 spins. Yeah. Yes. The Hamiltonian, yes, the Hamiltonian we use a double quantum, but then the precise values of the interaction depends on the chemical structure, the distances, and so on. Flap, yes, double quantum. Mm-hmm. It's really not a saturation value. It's because the coherence has already acted that we are not able to measure the details any longer. Yes. But that's a crystal. There is no saturation there. More or less here, this part will be this sort of saturation, which is the first part of the molecule. This is the sort of saturation, but then you are actually going go to the whole crystal, and it will go to the infinite, but then this saturation that you see here is because that we also study the decoherence, the more complex are the state, the fastest is the decoherence, which is consistent with the experiment. And essentially what that you're not able to follow the maximum number of correlated spin we have able to reach was about 10,000, but means that we reached 10,000 spins. And of course, there are systems, here they are again Loschmidt echo with a double quantum, the Loschmidt echo, but with a double quantum Hamiltonian, with the same Hamiltonian that is doing flop-flop and flip-flip. In a linear system, we have a hydroxyapatite. Now apatite is quite fashionable a few weeks ago because of this high temperature superconductor, which was not so. But it's a one-dimensional system from the point of view of our protons. In that case, in the one-dimensional system, the decay of the Loschmidt echo was essentially exponential. So essentially, it was not really many body, because it actually can be proved analytically, it's not many body at all. While in this crystal, I have this, it's not actually a Gaussian, that's a sigmoidal. I'm going to discuss a bit later on, but I have this. But this, I have the case that more that you mentioned. Here, it is a liquid crystal. In a liquid crystal, the molecules are oriented, but they are quite independent. So essentially, they don't see each other too much. So essentially, they're a system of finite number of spins. And then we see that essentially the number of correlated spins grows, that's the LE&OTOC. Essentially, first go to a part of this, I don't remember where it was, the tail, and then goes to the rest of the molecule. And finally, there are 16 spins, and that's the 16 spins, the size of the cluster that we see. A number of correlated, that you have the first portion, and then the other portion. And the Loschmidt echo also decays differently. At short times, when it has a decay in this part with a strong dynamics, it has strong decay. Then essentially no dynamics, no decay. where it stays without dynamics and no further mixing, no further decay. And then you go to the rest of the molecule. Again, you have more decay of the Loschmidt echo. That's in a liquid crystal where we have a finite system. Now we're doing scalings with a liquid crystal. We didn't do at the time, that is changing the value of the Hamiltonian and see how these time scales, this is time, changes with the Hamiltonian. And this is what we do now. Right. Yes. Right. Mm-hmm. Well, we will be with linear. I mean, in time, the size in a way, but then you have the number. It goes with the power law with the time. I'm going to show it. That's the sort of thing that we did now. In general, we started to do more pulse sequences to scale down the Hamiltonian. Essentially, what we do to scale down the Hamiltonian, again, we apply this pi over 2 pulses. We create Floquet Hamiltonians that essentially, that's the new thing. We create Floquet Hamiltonians that scale down the Hamiltonian. Scale down and change the sign. So we are able to change the time scale of the Hamiltonian. I'm going to be on time. So we did this. These are Floquet Hamiltonian. This, for example, is a different Hamiltonian. We scale it down, but applying a solid pulse. I mean, we apply radio frequency during a whole time, and we make the spins to precess at an angle with the external magnetic field. If you do it to evolving at an angle, then there is a projection in the strength of the interaction. As I showed you, the strength of the interaction depends on the angle between the pair and the external magnetic field. So if I define an external magnetic field which is at an angle, then I can scale down the Hamiltonian. This is with this sort of pulses. And then we have these other families of pulses where we do all the short pulses, and we put the spin in one direction and another to scale down the Hamiltonian. I'm not going to be to strength. That's a similar that I showed before, but it's an experimental. Again, that's at a given time, that's a number of coherence that get excited, and you see that it is essentially a Gaussian. And then, for example, this crystal where we have 16 spins in the molecules, but then in the molecule, which is the unit of the crystal. But since this molecule, this is adamantane, is almost spherical. It rotates permanently, thousands and thousands, more than 10,000 or at the second. So the interactions internal in the molecule cancel out. But they do not cancel out with the interaction with the spin in the other molecules in the crystal. So it's like almost an all-to-all interaction. That's a huge number of interaction because the 16 spins in the crystal, each one interact with the 16 in all the neighbor molecules in the crystal. So it's a huge number, but not internal ones. So the dynamics occurs from this excitation here, goes to the neighbors, to all the neighbors, but this huge number of neighbors, and we see how it's increasing the number of correlated spin as a function of times with this situation. Again, we see here that it goes with this diffuse. In this case, we use a Hamiltonian that has the flop-flop terms, the double quantum, but also has the dipolar terms. So the dipolar terms, we have this energy. It's different having this configuration of spins and this configuration of spin. They are like different energies. And this is sort of disorder, like an Anderson disorder. It's a dynamical disorder that prevents the system to go ballistically spreading. So it starts growing diffusively, and this is the law that we observe for this LE&OTOC, essentially a diffusive law. Number of spins goes with this with T to the 3 to 1/4, and it is perfect interaction. That's a recent article. Again, another case of another liquid crystal. I see this increase, the saturation here, and then the saturation to the number of spins in the crystal. So essentially, finite system. I have the saturation, here goes. We reach 200 spins, and then we don't have signal because the decoherence, what happens? I do the time reversal. Of course, there has been done decoherence, but since I have to do just the Fourier transform, I have to compare the time reversal with one phase, with another phase, and with another phase. I had to do the Fourier transform. I can use the Fourier transform in spite of the fact that the value is very small. So in order to do LE&OTOC, I can renormalize my signal from the Loschmidt echo. So the Loschmidt echo says how much signal do I have locally. While the LE&OTOC, this procedure, multiple quantum coherence, says this signal, how it relates with the phase that I put while it was a complex state. I put different phases. So as long as it responds to the phases, I can say how many spins I reach. But once the signal is very small, that's, I cannot say anything longer. So I cannot go further from this point here. Here there is no problem. That's already saturated because it's a finite system. So all the spins, all the decays that I say is a sigmoidal decay, that's a Fermi function, looks at same function. More or less, if we scale down with the strength of the interaction, they look much or less the same. And what the interesting thing is that essentially, I'm decreasing the strength of the Hamiltonian because of the pulses, but the error that I have is not scaled with these pulses. Essentially stays more or less constant because I scale the Hamiltonian, but the terms which are the residual terms are still there. So I'm able to change the time scale of the Hamiltonian with respect to the environment. So this sort of my errors. That's what I'm going to see. And I see again that this is scaled with the Hamiltonian. And this, when the Hamiltonian is 0, that's what I see. This decay of the Loschmidt echo is just from the environment. Because I made the Hamiltonian 0, and only that is left are these pulse sequences that I am applying. I'm doing a lot of things to get nothing in the Hamiltonian. I'm doing the same things. To have the Hamiltonian, to have different values of the Hamiltonian, I do the same pulses. It's only different values. And then I do all this dance to go nowhere, and that's why I have this decay. So this decay of the Loschmidt echo is just of these residual terms. That's our way to know the residual terms. And then we do the decay of the Loschmidt echo, one of the T3 for different Hamiltonians, that the time scale of the irreversibility, related to the scale of the Hamiltonian. That's universal curve. So all those points says, how is the irreversibility that I observe with respect to the Hamiltonian? And what is the value of the environment with respect to the Hamiltonian? T2 is the flip-flop term, is the time scale of the Hamiltonian. Then in principle, I will expect to have a curve which is a line here and go to 0. So 0 environment, 0 decay. 0 environment here will be 0 decay. Still, once I put all the points there, I see that I go to the finite value. Now I have really an experimental realization of this thermodynamic limit. I go strong Hamiltonian as compared with the environment. So I have the two time scales of the Hamiltonian and that of the environment. And we have different pulse sequences, so I have different errors and always have here. That's quite universal again. And what is the time scale? It's essentially 6 times T2. That's the value that I observe here. That's a perturbation-independent decay of the Loschmidt echo, and the perturbation-independent irreversibility. That's the central hypothesis of irreversibility. We did further experiments. We did, for example, with this experiment again, we did another complete sequence of pulses. That's different nature of the errors, and we have the same value here. And I was to mention what is the decay of this Loschmidt echo. At some point, we did just a hard spheres gas, and we did Loschmidt echo classical in the hard sphere gas. In the hard sphere gas, what we observed, the Lyapunov exponent of the system of hard sphere in the Loschmidt echo also manifests in a sigmoidal wave function. The Lyapunov exponent is also the exponent here, not the initial time. So you have an initial sphere, you make it to evolve, and you ask whether you forward in time, backward in time with a slight perturbation, and you ask whether this sphere came back to the original phase space volume. And this is what you are computing here. And this depends essentially of the phase space volume that you take, and then the exponential is in this part. And again, it's not only clear here, that's probably have a different resolution. The same occurs when you do the Loschmidt echo, that's Manfredi and Hervieux. They did a Loschmidt echo in the Gross-Pitayevsky model, the variations of the Gross-Pitayevsky models, which is also has instability. And what they observe against their curves like this, where the Lyapunov exponent manifests in this part of the decay. What they associate with the Lyapunov exponent. And again, I have a more experiment, even these things as if we finish this year, there's still a dynamics which is only double quantum. Until now, I was having a dynamic which is diffuse, essentially diffusive spreading, and this is double quantum. And when it is double quantum, that will correspond to a ballistic spreading. So there is no sort of disorder, this term which is opposing the dynamics, the competing with the flop-flop processes, and then goes much faster, that corresponds to the ballistic spreading. So the number of correlated spins is a ball that is growing linearly with time. And that's the exponent that we observe here, that essentially is a t to the 3 that corresponds to this ballistic time. Again, interesting that this double quantum Hamiltonian, and this is XYX, that means that the Zeeman is in this direction, in a sense, the Ising term is in this direction, while I put the spins in the Z direction. That's what means this. This and this essentially go to the same, which are different Hamiltonians, different pulse sequences, same crystal, go to the same, essentially, asymptotic value. That's a result from this year. So these are the LE&OTOCs, how the information is spreading in the Hilbert space. And this is a paper that appears just in June. Brian Swingle, he is here with the Loschmidt echo, and he claims to have solved have solved the scrambling. So in order to do this many-body scrambling, he uses a sort of quantum circuit that is a simulator. It's still not a real dynamics of the multi-spin system, but has a code which approximates the growth of the LE&OTOC. And with this law that depends again from this ballistic, diffusive, and different Hamiltonians, that's what is having here. Here there are experimental points. I don't remember if these are the minds or my students, and this numerical simulation. That's quite, but still, this is the LE&OTOC. But for me, the LE&OTOC is trivial. The point is the time reversal of the LE&OTOC. Whether this complexity that you reach allows you still to come back. So the main question, the central hypothesis for irreversibility is only has this my experimental hint. There is still room for this. So until now, so people think that this dealing with irreversibility sounds quite strong, and they want to get into polemics. But essentially, what I'm saying is essentially, in finite system, the auto commutator saturates for finite system. That's what I say. The auto commutators, and again, auto, there are many different autos. Depends on what are the operators that you put there to commute. For me, autos are those things that are correspond to the quantum coherencies. There are particular ones. These keep growing until they are in unbounded systems, and the precise law depends on the system. On the system and on the Hamiltonian that I implement, that is this. Of course, in single particle systems, the theory and numerics shows that the Loschmidt echo of the case is exponential, that with the classical Lyapunov exponent, but we don't have a theory for the real many-body system. The experiments are still puzzling. So again, there's depends on whether you are doing the dynamics in a situation where the spin projection is being conserved. This is when the spin is conserved, is what I would call exceed Hamiltonian. Well, I don't have a universal notation here, so like I was having with transfer, no conserved polarization, and that's now I call this. That's a standard dipolar Hamiltonian with polarization is transferred, then it's not going to be conserved. That's the situation. While under double quantum ballistic, that's always this logistic curve. And if it is this conserved, this is the Gaussian curve. And it is one-dimensional system. It is in that case, it is an exponential. I don't know whether to identify this exponential with a sort of Lyapunov exponent. But for me, what is very important in all numerical simulations is not the same, this limit is not homogeneous. I mean, it's not the same having an observable, which is the Loschmidt echo, in the limit when the environment goes to infinity or remains, no, that's wrong. Environment going to zero, that's has to be a zero. That's I have another transparency. They go into zero, and then the number of particles go into infinity, that having the number of particles go into infinity and sigma go into zero. So that's a problem. So for my point, I mean, I will say that the Schrödinger equation may have this unstable limit in the many-body case, far from the ground state. In the ground state, I mean, the levels are separated, you can have gap, and that could be robust. But once you are there with this density of states, which is so dense, anything that you do will completely spread, and then will be no more important. I mean, how is this anything that you do, how big? So, many people here is a phrase from Steven Weinberg, again, because I didn't put the proper resolution here. He said that the Lindblad equation that contains the Schrödinger equation for ordinary quantum mechanics as a special case, but in general, this equation involves a variety of new quantities that represent a departure from quantum mechanics. These quantities, whose details, of course, we don't know, though it has been scarcely noticed outside the theoretical community that there is already a line of interesting papers by Girardi, Rimini, Weber that propose fluctuations in the Hamiltonian, say that essentially that's what are going to give irreversibility. So my point that they don't realize, again, the question of the thermodynamic limit. For me, it's not the problem of the Schrödinger equation of a single particle, but the Schrödinger equation of n to infinity particles. That could be unstable. It's not the same as an hydrogen atom or a molecule or a small spin system. And I'm just in time. Yes. Okay. Or let's try. Will be. Yeah.
It's just a small detail
Mm-hmm.
there when you say Loschmidt echo is perturbation-independent Gaussian. What do you mean by Gaussian in this case?
The Gaussian decay, that's essentially that. In this many-body system, it is quite rare to see an exponential decay of the Loschmidt echo. I see the Loschmidt echo, it's this Gaussian, so the time scale, this is what is perturbation independent. That's time of the reversibility time. In the classical system, I'm sorry, one-body system, you expect to see exponentials here.
Okay, thank you.
Can you go back in your slide?
How much? Where?
I think 5.
Hmm?
Go
Still?
more.
Well, remember?
Is there?
Mm-hmm.
Why is negative signal negative?
Okay. You're looking, so spin is not, projection is not conserved in this system. That's, so it could be, you can measure something which is negative. That means that the local signal that you observe is inverted.
Okay.
Mm-hmm.
Thank you.
It was already on.
At the beginning, you gave as example the MRIs, the NMRI.
Mm-hmm.
And for the cases in which you inject some gadolinium or some other to have the contrast, how is it done with when they look at the active neurons or the active part of the brain?
Well, they look the oxygen signal. That's
Sorry?
Oxygen. And that's that they are consuming oxygen, that's a metabolic process of oxygen, that's what they are detecting in real time.
All right, thank you. Anyone else?
So before we didn't, our first experiment of this time reversal involved putting a radio frequency and so irradiating the sample. So it was not possible to do, not conceivable to do it in a living object, only in a material. But our more recent pulses, we do time reversal with just these pulses, which essentially do not involve power. So again, could go many decades before it's been implemented T3, because all the processes are very slow. But essentially now it is conceivable because they are just pulses, not not irradiating power into the patient.
Thank you very much. I guess. Okay, thank you. Let's go for lunch.